My name is Ville Kilpeläinen. I have worked here at the University of Helsinki Sustainable Chemistry Research Group for almost a year now. Today I would like to tell you about the research we do, and also you will get to meet the people behind it. First, I would like you to meet our professor Ilkka Kilpeläinen, who will give you an overview of the research we do. After which, we're going more into the details and go through the process of developing a new super base to be used in ionic liquids step by step.
Oh, hello. My name is Ilkka Kilpeläinen and I welcome you to follow what we do here at the Department of Chemistry, University of Helsinki. What we are working on is basically cellulose dissolution, and the cellulose means basically paper pulp. It can be used cotton clothes or anything which is related to cellulose. It can also be like yesterday's newspaper. And what we are working actually is something called ionic liquids, and especially superbase-based ionic liquids. And the aim is really to go into industrial scale with these molecules. If you asked me a couple of years ago what was in a way our target, I would have given a little bit suspicious answer to that question, because when you are actually working in the laboratory, you're quite far away from optimizing certain property in a really big scale. Typically we work with few gram amounts, but actually what we are doing currently is that we are easily working with several kilograms or even higher amounts of molecules. And there are certainly some selection criteria how can we actually pinpoint those important structures and why we are making this selection, and we will try to explain that process to you today. And actually what we are doing is not just the organic synthesis, but we are of course characterizing the molecules in terms of their price, in terms of efficiency in getting them, in terms of their safety or toxicity, and all other kind of interesting parameters before we even can think that we are actually going into a larger scales.
Here we have a molecule called TBD. It is based on a natural substance called guanidine, which can be found in living organisms as a protein metabolite. To this guanidine part, consisting of 3 nitrogen atoms and a central carbon atom, 2 hydrocarbon rings are attached. This forms a prototypical structure on which the superbases we are working with are based. By adding different substituent groups to this molecule, or by changing the size of the rings in the molecule, we can produce potentially hundreds of thousands of different compounds. And by mixing these compounds with acetic acid, we can produce ionic liquids, some of which have potential use as solvents. The first step in the process of developing a new superbase for ionic liquids is to design a structure for the molecule. When we know what kind of molecule we want to have, we have to find a way to actually prepare the molecule or to synthesize it. This is similar to solving a puzzle, like this one I have here, for example. To solve the puzzle, we have to put the pieces together in a correct way to create the object. Likewise, our work as chemists is to put together atoms to create a molecule. Our PhD student Eva have been designing these molecules and synthesizing them. And next, she will tell you more about this process and her work.
Hi, I'm Eva Gezania, and I'm a second-year PhD student at the University of Helsinki, and I'm working in Professor Kilpeläinen's group. My work is focused on the synthesis and the design of the superbase that we are using in our ionic liquids. So it works as we have a reference molecule, and from this I have to design some derivatives. So it can be more than one. The good side of this is that I can change the size of the molecule, I can change the derivatives on it, or the groupment of it, and we can end up with hundreds, thousands of derivatives. So the part of the job is to select what kind of derivatives we want to make, to focus on what kind of characteristic of this reference we want to improve. It can be the cellulose dissolution, it can be the stability, it can be many, many things. Once the derivatives are synthesized, from here we test the cellulose dissolution, we test the stability, and we characterize it. Once this is done, and we are happy with the molecule and the behavior and the stability and everything, we have to focus on the routes that we use to synthesize them, because from this side we scale up to a certain level in this lab. So it means that this route has to be easy, it has to be cheap, it has to be non-toxic, so green, to be able to scale up this. And from this scale it goes to another step.
Now then, here on the table you can see some new superbase molecules from Eva's lab. If these molecules are to be used in ionic liquids, they must have properties that make them suitable for this use. Some of these properties we can predict quite accurately even before synthesizing the molecules. Others, however, are more complex, and therefore at this point we have to study the molecules so that we can characterize them. Take this molecule for example. It's a good solvent for cellulose, it has a low melting point, but when we introduce some water and heat to it, it will just break down and hydrolyze. So in this case it's not gonna be a good solvent for cellulose, as it will most probably be destroyed in the cellulose regeneration process. Another very important quality of an ionic liquid is its toxicity. Although the compounds we are working with are generally quite safe, there is always a possibility of unexpected toxicity, and therefore each compound has to be studied for toxic effects, as we want to filter out any possible toxic compounds in an early phase of the development. Think about this compound for example. It looks good on the outside, but when you take a closer look and open the lid, you can find out it's actually quite hazardous. So it's better to keep this one in the lab as well. Now, let's go meet Sini Santasalo, who will tell you how she measures the toxicity of our superbases.
Hi, I'm Sini Santasalo and I do ecotoxicity measurements for the superbase ionic liquids. Ecotoxicity measurements are needed because we want to confirm that our superbase ionic liquids are good for the environment. The model that I use is based on bioluminescent bacteria. The bacteria, when they feel great, then they send light, and when they die, then they stop sending light. So I give different concentrations for the bacteria, and then I see where is the limit when 50% of the bacteria are dead. When I do the ecotoxicity measurements, I have to know what kind of sample I'm analyzing. The purity of the sample is really important, because if there is one impurity that is really much more toxic than our superbase ionic liquids, you can easily see that in the results. So I need to do analysis for the sample that I'm using in the toxicity measurements. In most cases, I start with NMR, and addition to the NMR, I use chromatography, for example, HPLC and GC. The superbase ionic liquids seems to be harmless, and that is really important. Of course, this kind of ecotoxicity measurements, this is just one model, and of course there can be some differences in the toxicities for bacteria and humans.
Now, after we have filtered out any compounds with unsatisfactory properties, we are left with only two molecules on the table, both of which make really nice ionic liquids, and they are both non-toxic. If these compounds are to be produced in a larger scale, however, it is not enough to get the chemistry right, but the production of these compounds must also be economically feasible. Think about this molecule, for example. One of the pieces is made out of pure gold, making the production really expensive. So it's best to keep this one in the laboratory until we can find a cheaper way to produce it. The cost of the raw materials isn't the only expense in the production of chemicals, however, and the process used in the production must be considered as well. Fortunately, our PhD student Jussi Helminen found a really straightforward way to produce our main superbases from cheap and commercially available raw materials. Next, we will go meet Jussi and see how he scaled up his synthesis.
The apparatus we have here is used for preparing superbases for ionic liquid synthesis. The favorable thing about this synthesis is it is very straightforward and thus amenable to scaling up or preparing larger amounts. Originally, when I started this work, what I used was just a small flask in a fume hood with some related glassware. Over time, I needed to prepare larger amounts of the materials because the synthesis was decently good for the purpose. And eventually, we ended up with this, what we have here. It is the current setup that we use. In fact, it is quite surprising to end up doing work like this in a university setting. I never expected to end up doing such work, but having read literature related to industrial organic chemistry for a while, it has been very exciting. From point of view of biopolymer processing, people often ask if it is even viable to use ionic liquids for industrial purposes due to the price. In our case, there are some favorable features about the things that we are working with. The current synthesis of our main superbase consists only of 2 steps, which are very straightforward to carry out. Thus, the materials used are not, in fact, very expensive, which makes the ionic liquid relatively cheap. Furthermore, in this case, one of the original reasons for studying these ionic liquids in particular was the fact that they are distillable and can be purified. At least it is feasible to carry out industrially. I have seen the same method used on much larger scales than what we have here, but we use it to prepare materials that are used in research to provide our collaborators with materials for their work and support them in that way. Also, the superbase can be used not just to prepare ionic liquids for biopolymer purposes, but also for catalytic purposes.
Now, although the process described works really well even at larger scales, there are some inherent disadvantages in using batch processes in general, like slow heat and mass transfer that can lead to prolonged reaction times. Also, such processes can be quite laborious compared to flow chemical processes. Therefore, we have researched the utilization of continuous flow chemistry for the synthesis of our main superbase. Next, we will go to the laboratory and I will show you what we have accomplished. Here you can see the results of our hard work and research on continuous flow processes. A fully functional pilot reactor capable of producing at least 1 kilogram per hour of a superbase, which is an intermediate product after the first step of the two-step synthesis of our key superbase. Most probably, the reactor is capable of much higher throughput, as at this point no optimization have been done on reactor parameters and reaction conditions. The reactor works by combining the operational principles of reactive distillation and a plug flow reactor. By using a distillation process in the reactor, we can maintain a favorable excess of one of the reagents, even though the stoichiometric mixture is fed into the reactor. Fast mixing of the reagents reduces side product formation. The distillation process also purifies the product inside the reactor so that the product is pure enough to be used in the next step of the synthesis without any further purification. The reactor might seem and look really complicated. However, using it is actually much easier compared to doing the synthesis as a batch process. All we have to do is to turn on the power, and while we wait for the reactor to heat up, we fill this bottle with a reagent mixture, and as the reactor has warmed up, we turn on the pump and sit down to wait for the reactor to do its job and fill this bottle with the purified product. Now then, here we have a molecule that has passed all the tests. It forms ionic liquids that are good solvents. It is hydrolytically stable enough. It is non-toxic. In addition, we can produce it in large scales by using efficient processes and cheaply available raw materials. However, our work as chemists is not done yet. In the chemical space, there are endless possibilities waiting to be discovered and millions of compounds yet to be found. Therefore, we will continue our task to find these molecules with new and exotic properties.